What if I told you there is a way to connect points to a map using the least amount of roads possible? That's the magic of Kruskal's algorithm. Whether you're a budding programmer or just curious about how technologies solve real world problems, this video is for you. Let's explore this algorithm, how it can save time, money, and resources, making our world a little more connected. All right, now that we know how we have the intro, let's dive into the problem at hand, finding the minimum spanning tree MST using Kruskal's algorithm. Now this might sound a bit technical at first, but don't worry, we are going to break it down step by step. So what exactly is a minimum spanning tree? Picture this, you have a network of cities connected by roads and you want to connect all these cities with the least amount of road work possible. That's essentially what an MST does. It connects all vertices in a graph while minimizing the total edge weight. In simple terms, we want to ensure that we are spending the least amount of resources to connect everything efficiently. Now let's dig into how Kruskal algorithm helps us to achieve this. At the core, Kruskal's algorithm is a greedy algorithm. This means it makes a series of choices, each of which looks best at the moment, with the hope of finding the global optimum. In our case, it repetitively picks the smallest edge that doesn't form a cycle in the growing spanning tree. Here's the breakdown of the key concepts we'll be working with. Number one, edges and weights. Each connection between vertices is an edge, and every edge has a weight representing the cost to traverse it. Our first step is to gather all these edges and sort them in ascending order based on their weights. This way, we can always access the cheapest connection first. Number two, union find data structure. To efficiently manage and track which vertices are connected, we use a data structure called union find or disjoint set union DSU. This makes us determine whether adding a specific edge will create a cycle. If two vertices belong to the same set, adding that edge would create a loop which we want to avoid. Number three, path compression and union by rank. These are optimization techniques we use within the union find structure. Path compression helps flatten the structure of the tree whenever we find the root of the vertex of a vertex, making future queries faster. And union by rank ensures that when we combine two sets, we always attach the smaller tree under the root of a larger tree, making the structure balanced. Now let's outline our approach before we dive into the code. First, we'll create an edge class to represent each edge in our graph, including its source, destination, and weight. Then we'll set up our union find structure, which will include methods for finding the root of a set and for merging two sets. Next, we'll implement the core of Kruskal's algorithm. We'll sort our edges, iterate through them, and for each edge, we'll check if it forms a cycle with the already included edges. If it doesn't, we'll add it to our MST. Finally, we'll keep a running total of the weights of the edges we include in our tree, which will give us the total weight of the minimum spanning tree at the end. And by the time we are done, we'll have a clear understanding of how to efficiently connect our graph with the least cost possible. Alright folks, today we dive deep into the world of graphs with Kruskal's algorithm to find the minimum spanning tree MST. We covered the essential steps from defining our edge structure to implementing the union find technique for efficient cycle detection. Our code solution meticulously sorted edges by weights, used path compression for quick root finding, and efficiently united subsets to ensure we build the MST without any cycles. This results a total weight of the MST that optimally connects all vertices. Remember, the key takeaway here are the importance of sorting edges and understanding union find operation and how they come into play when constructing the MST. If you found this content helpful, don't forget to give it a thumbs up and subscribe for more exciting coding challenges and algorithm explanation. Make sure to check out the source code link in the description below and stay tuned because in our upcoming videos will explore Prime's algorithm, another powerful methods for finding the MST and see how it compares to Kruskal's. You don't want to miss it. Until then, keep coding and keep pushing those